Swayam Prabha. Digital India. Educated India.
Okay, so the takeaway for you, at least, even if you have lost the details, is that if I did finite element method, I can convert this differential equation into another linear system. It's not the same linear system as the finite difference method. It's some other linear system, but I can write down the linear system, and you can think of this as a black box if you're in an application domain rather than working on solving these problems. So here is an example. I didn't do this for finite difference, but here is an example for solving this simple enough problem. I start with sine pi x, I derive the write the second derivatives, write down the f of x using this finite element method. Okay, and both the computed and the analytical solution, this is the true solution. I've plotted both the computed and analytical solutions, but you can't sort of see there's a little bit of blue you can see. It's even for such a simple mesh on 0, 1, which consists of like 11 points, it gives you it sort of visually gives you a really good approximation of the true solution. And for some purposes, if you're interested in its derivative, this is the derivative. The derivative does have a step behavior, something you might keep encountering if you do graphics processing. Sometimes you'll end up with these stepped reconstructions of surfaces and so on. But so this derivative of u also has this feature if you want to use the derivative for any purpose. Okay, and then here is a 2D example of this. Okay, so and here there is a few things that I have to talk about. So my 2D problem is this right-hand side function. I have something which I can derive from this solution. It's going to be something like some 4 pi square. No, it's going to be some pi square times sine pi x, sine pi y, or something like that. Okay, you can write it down. It's not important. But if this is the true solution, I can compute the Laplacian and obtain a right-hand side and use this black box idea, if you want, of solving this problem. Okay, and now I see for the first time I see an advantage with this finite element method. Okay, so from the 1D perspective, it looked almost the same. Yeah, I mean, I had these intervals, whether I was doing finite difference or finite element, and it's kind of the same thing. But in 2D, I see this difference. I can now take the square. I don't need to put down those uniform lattice grid points. Instead, I have a mesh, and I'm sure you have encountered enough about meshes already in the course. So I don't have to explain meshes, but the interesting point is I have to explain how the hat function generalizes. Okay, let me see. I forgot to put a picture for it. But essentially, if I looked at this particular one ring, the hat function's generalization is that it's really going to be like a tent function. It's like I have erected a tent by putting nails at all these points, and I've taken this point to be at value 1. So I would recommend you to please take a look at it by going to Math World or Wikipedia later. Yeah, this is my bad. I should have put a figure here. Okay, showing you what the tent function looks like. Okay, but it's going to be something like this if I looked at it in a projected view. Okay, except now it's going to be defined not on these intervals or on lattices, but on these meshes. And again, this is equivalent or identical to saying these are the barycentric functions on these triangle meshes. Okay, so I presume you know what meshes are, and I've solved this problem on this mesh. I can do integrals on each of these triangles, no problem, and I can set up that linear system matrix and the right-hand side corresponding to the f derived from it, and I have the solution here. Okay, so I've just plotted the solution. Ignore the title for the moment. It's not very relevant, but this function, at least I can visually check if it's correct. Okay, so this is sine pi x, sine pi y, which means if x is 0 or y is 0, this function is 0. So for x equal to 0 or y equal to 0, indeed, the blue, hopefully you can see the color, the blue color is 0. And for x equal to 1, y equal to 1, again, the boundary condition is 0. So indeed, this has the correct boundary conditions. Um, and it does have the correct behavior, like at half it reaches its maximum value, which is 1 sine pi over 2 sine pi over 2. Okay, so this part is like, you can think of it as a black box for two-dimensional meshes. Sometimes you might deal with three-dimensional versions of this problem in graphics as well, but in either case, feel free to use a graphics library like libigl or whatever else, Seagull or whatever your either institute or your workplace requires you to use, and you should be able to find the solution without worrying about the nitty-gritty details, but knowing that you're doing a better job than finite differences. Okay, so I'm going to take a pause again to see if there are further thoughts, questions.
Can you please go to the previous slide?
Sure. This one?
No, probably one more.
Let me know when to stop.
Yeah, this one, yeah.
Okay.
From KU equal to B, we went to KU equal to MF.
Yes.
Okay, and that was how you divided that whole that whole space into VIs. V from V of X into VIs. That was the aim for that.
Okay, so for now, ignore the VIs. Okay, so it's needed. It's for all VIs, and therefore it sort of is a dummy variable. But what I did here is this, as like I explained. This leads to this problem. Okay, and this matrix essentially consists of elements which are integral 0 1 phi j I prime phi I prime. Okay, the right hand side vector B consists of elements which are like integral of f times phi I, and f is some could be complicated function. So here what I've done is I've approximated f. I mean, we are doing approximations, so we can do one more layer of approximation. What I've done is I've represented f in this basis. So even if f is a complicated function, I've written down its linear projection or projection into the space of linear polynomials, piecewise linear polynomials to be precise. But yeah, I've approximated my given original right-hand side function by a function that is representable in this basis. And now these fk's are just the values of f at each of the grid points, which is like a number and comes out of this integral. And I now have an integral of the basis functions. This integral is called as the mass matrix. There are many approximations graphics people do for this mass matrix. So, but this is the mass matrix in finite elements, which is why I now have m times f, where f is the vector of values at each of these grid points.
Yes. Okay. Now when we go to the 2D case.
Yes.
Yeah. So here how will the mass matrix look like?
Great question. Some hint. There's a hint of it in a later slide. Okay. For this purpose, for now, in finite elements, it's going to be some. And let me use the whiteboard. So mass matrix in. Oh boy, okay, I got kicked out of the meeting in my pad. Let me quickly join again.
Can see your pad in the meeting, Kaushik.
Can you?
Yes.
That is weird. I've lost it on my. I don't see the whiteboard anymore on my iPad. Okay, but that's okay. So let me share a new whiteboard. Create new. Okay, so mass matrix. Yeah. So if I could share some other document than a whiteboard, it'll be way better. Let me. Sorry, folks. Give me 30 more seconds. Don't want this. Go back. No. Share photos box. Share screen. That's much better. Start. I'll do this. Okay. Now I can do what I like. Okay. So this is what I prefer. Okay. So mass matrix for FEM in 2D. So that is the question. And maybe now I can highlight, show you what the basis function in 2D looks like as well. A figure I should have added to my slide, but basis function phi in 2D on a triangle mesh. Let me first show you that, and hopefully will make something easier. So imagine this is a triangle in my triangle mesh. Okay, so this is Vi, Vj, Vk, and my phi k, I'm going to draw phi k, is going to be value 1 and 0 here. Okay, so this is kind of, one needs to imagine that this triangle is lying in some xy plane, and the blue color value is height up above this plane. Okay, so the triangle is in the xy plane, and this blue value is height above it. Okay, so this is the tent function for a vertex in a triangle. So I can write this down as is the same idea. Phi k on some other xj is value 1 if k equal to j, 0 if k not equal to j. Or so there are three of these tent functions. This is tent, hat, barycentric. You could call it. It has many names. It's polymorphic, therefore. So this is the barycentric function at vk, and there would be one at vi and vj as well, which I'm not drawing, but there will be ones for vi and vj as well. So a given triangle therefore has three basis functions, and these are the lowest order bases. Remember, in the course of my presentation, I kind of said or convinced you folks, hopefully, that it's enough to consider these lower order ones for graphics processing. So these are the lowest order ones. A given triangle in a mesh has three lower order basis functions. Okay, that's what it looks like. Now I can take a slightly different view, and I consider this ring of triangles. This central vertex is V. So this is part of, sometimes called as a one ring of triangle. And I can now ask, what does the basis function look like? It's hard to draw, but we can try nevertheless. It's value 1 on top of this and 0 everywhere else. This is starting to sort of look like a tent if you stretch your imagination. Okay, this value is 1. Therefore, this basis function I showed you above for the triangle is essentially the restriction of this basis function on a one ring of triangles to a given triangle. So I might call this, this could be part, this is my triangle, vertex Vj and Vk. And okay, I did Vk there. Maybe I should have done Vk here too. So this is Vi, Vj. So this triangle Vi, Vj, Vk is part of a one ring, and the basis function looks like this tent around these one ring of triangles. This again is P, Vk. Okay. Now, what is the mass matrix? The mass matrix is essentially the same mass matrix in 2D. It's the same in any dimension, to be honest, as an expression. The mass matrix entries are going to be things of this form, Mij, where Mij is the integral. Now I have to integrate on the two-dimensional region, which is essentially the triangulation, the triangle mesh. And I'll have something like phi I xy if you want, phi j xy dx dy. Okay. Where omega is the region of the triangulation. So the triangulation itself is part of some bigger region like that square that I showed you, and I have to integrate this product of basis functions on the whole region. But fortunately, these functions are compactly supported. Phi's are compactly supported, which means outside this one ring, they are just 0. If this triangulation extends in the plane, I could have more triangles going along. But my blue basis function is just 0 everywhere. It's 0 identically outside this region. Okay, it's a 0 value. Therefore, this integral slightly is simplified. It's going to be an integral on all the triangles incident on that vertex for any phi I, phi j, and then you can do some algebra and try and determine that if phi I and phi j will be coincident or not, or partly coincident, and you can do a little bit of jugglery and figure this out, that this will be an integral on only some finite number of triangles. So this Mij would therefore become summation over some E in the support volume. So I'm calling E as, okay, let me say P as the triangles in the support of phi I union phi j, which is fancy symbol for saying, okay, find all the triangles where phi I and some other phi j are together non-zero and just integrate over those triangles. Okay. This is still this two-dimensional integral if you want. So this is the finite element mass matrix. And then there are approximations to it. But this is the true finite element mass matrix, which comes out of the integrals of these barycentric functions or Lagrange basis functions or hat functions. Okay. And maybe for that completeness, I'll just write that mass matrices can be approximated. And you might think, what can it be approximated by? You could approximate it by a diagonal matrix instead of having a big mass matrix like this. You could possibly consider doing that, and people then would use these functions to be value 1 on some Voronoi regions inside the mesh and compute the mass matrix on that Voronoi region and so on and so forth. Or you could use the barycenters of the triangles and write down an approximation for this integral. Again, there's some references to all of this coming up in the slides, but the true blooded mass matrix is this object. Okay, hopefully that answers the question to whoever was asking, and we could move on.
Yes. Yes.
Okay, I'm going back to my slides. Okay, so this is what we were talking about, and okay, so this is the stiffness matrix. This is the left-hand side, which we did not discuss that much, but in 1D, we sort of wrote it down. It was derivatives, products of derivatives. In 2D, if you're willing to buy that generalization, derivatives become gradients. And so there is a dot missing. These are both vectors. So it's the dot product of these gradients that you integrate over the whole region. Okay, the region is also missing. Okay, so the finite difference method for this problem, not this problem, in 2D, where we had this grid, has a stencil that looks like this. By stencil, what we mean is essentially some of these quantities are going to repeat. And I can go back to it, but I'll let you look at it when the slides are with you. But you can kind of convince yourself. This is the standard 5-point stencil where there's the north, south, east, west point is what some people would remark about the stencil. This is the standard stencil for the Laplacian in 2D in using finite differences. These two matrices, we saw sort of even looked at it in my handwritten part. These matrices, you have no hope that they are even related. Okay, yet these can be with some kind of either you do finite elements on grids, or you extend the notion of finite elements to triangle meshes. Things we are not doing in this today, but if you're willing to somehow go along with that argument for the moment, these two matrices, which do not look same at all, can be related. And in fact, they can be exactly the same. Okay. In fact, in 1 dimensions, which I did not write down, but if you did this as an exercise, you computed this matrix in 1 dimension, you will get back that 2 minus 1, minus 1, 2, minus 1 matrix. Okay, so that was the matrix we had. Okay, I will go back a couple of slides. This was the matrix we have for finite difference. If you sat down and carefully computed the mass, you don't have to carefully compute, you just need to compute it for 2 intervals and convince yourself that you'll get back this 2 minus 1 minus 1 matrix. In 1 dimensions, the finite difference and finite elements matrices coincide. This was the 2-dimensional finite difference matrix, but I'm claiming something slightly different. I'm saying that if you're willing to do finite elements on grids, or you extend the definition of finite difference somehow, you hope or believe that someone has done it already, to triangle meshes, the stiffness matrix that you get, the left-hand side system matrix, will be identical. And this is some sort of a feature of the lowest order method. It's not something incredible. It's an interesting, you can make arguments for this coincidence, but it's a feature in 1 dimension and 2 dimension. It's not true even in 3D. Okay, there's no way to make the 3-dimensional finite difference and finite element matrices ever coincide, even if you do this extended finite element on grids or finite difference on 3-dimensional meshes. Okay. So here I'm saying for the polynomial basis, you can compute these quantities analytically, or you can just take the easier way out and throw it to a numerical integrator as well. There are these things called as performing numerical integration on simplices, on 1-dimensional regions, 2-dimensional cells, so on and like so forth. There was a 2010 paper that sort of does it very nicely and reasonably efficiently for any n-dimensional simplex. It's called Xu and Gimbota, XU and GIAMBOTTA. Again, if I'm happy to throw these references into the slides itself when I give you the final version. I can send you an initial version first, but I can sort of throw in some of these references into the slides themselves if you care about it. There's a method that came out in 2010, which is like quote unquote now at least widely used in the finite element community for computing integrals like this. But the graphics community doesn't have to really know about it because we're not going to do anything beyond the lowest order case in any case. Yeah. Okay, so in fact, graphics people popularize this, that you compute the stiffness matrix, which consists of integrals. You can sit down and do some geometry. You write down these triangles, write down the gradient of this function of the hat function that I showed you in my slide, in my writing. Just like this hat function has like a constant derivative, it's positive and negative. The 2-dimensional hat function has a constant gradient. Okay, so not too surprising because it's a linear function. Phi is a linear function. So we can sit down and patiently write down all this for a given triangle and use high school geometry and notice some relationship between what we compute. If I computed it generally, not for some general triangle by putting in, x0, y0, x1, y2, x2, y3 as the coordinates maybe, or write down some altitude, heights, and so on and so forth for the triangle. I can do some basic high school geometry and obtain this stiffness matrix via a geometric quantity. Okay, what do I mean by geometric quantity? Via some areas, lengths of triangles, areas of a triangle, or length of some segments within the triangle. It could be the altitude, it could be some circumradius. There are some of these basic things that high school geometry tells us about on triangles. And then there are some angles, and in particular, it involves the cotangent of some angles. And graphics folks tend to use this alternative yet equivalent version of computing the stiffness matrix. Okay, so this is a geometry. This only depends on the geometry. If I give you the mesh, I don't need to know what these integrals are or anything like that. I can write down the Laplacian's discretization, which is equivalent to the discretization by finite elements, by just writing down this cotan matrix. Okay. And like I said, it's related to geometry. And the triangle version, I don't know, it's kind of lost in the annals, I think, but there's Poltier who uses it in late 1980s or early 1990s. Pinkol and Poltier are these two people. Poltier is at the Free University of Berlin in Germany, I think. In 2D, it's been around for 20, 30 years, the Cotan matrix, although you could trace it back further as well. But at least I know the history of it from these 80s and 90s. But recently, Keenan Crane, recently as in a few years, with like 2 or 3 years ago, Keenan Crane has who's a computational graphics person at Carnegie Mellon. He has a version of the Cotan formula involving so-called dihedral angles for 3D. And at least to me, it was new. I was not aware of it before Crane posted his preprint or version of it, in which he also says you can compute it for any n-dimensional mesh. So you can compute the discrete Laplacian, not just in 2D or 3D meshes, in any n dimension, which finite element people, for instance, know how to do using these integrals and so on. But I think he claims to do it using this geometric expression for any dimensions. Therefore, it's a useful thing. It's a useful formula. It's useful to know. And we'll talk, here is the formula. We'll talk about it for a little bit now.